we're going to introduce Neil Billett into the equation later on, because I don't think it's quite right just for a structural engineer to be speaking on a subject as big as this. Neil Billett's a key environmental engineer in the practice in Buro Happold, which is where I work, and I want him to join in towards the end, and maybe in any discussion that we can get going later on. But for a while it's just going to be me with all this technology to master. Apologies for the delay getting going. It seems a bit cliched really to say that we're on the edge of a revolution, but the more I think about it and look at it, it feels like we are. And then, of course, you realise that I suppose change is so fast now that it's just one long spiralling revolution of change. I'm not sure that it's really having the impact we'd like in the construction industry, if we call it something as unglamorous as that, and it's worth maybe looking at why. So what I want to do is spend some time looking back and then looking forward, looking back at the way, what are the influences that have been affecting the look of the built environment, the shapes of things that we build, why we build them out of what we build them, so that when we then look to the present and on to the future, we can think about how will the new materials of the future impact on what we're building. I mean, particularly, what are the new materials of the future? How should we be looking to influence them if we can, and so on. So if I can start. Okay, it's called Forming the Future. It seemed to me, been giving this a bit of thought, it seems to me there are some fundamentals to what it is that influences the way things are that we build. To me, it's the material we build from, our ability to handle that material, whether that's a mechanical ability in terms of the tools we use, or a mental ability in the way that we describe how to do things to each other and through teamwork make something happen. And I think it stretches into our ability to design, our ability to predict behavior through analysis. So it's a kind of understanding thing. And our needs, of course, there's no point doing anything if there aren't people with needs for it. So I thought it was worth looking at the past and the future in those terms. Simply put, with what, how, and why. And then getting into a little bit more detail, with materials it's about getting them from somewhere on the globe, changing them in some way, in a primitive way or a sophisticated way, and then using them. Our ability, it's about ability to imagine, ability to describe to each other, communicate, and then ultimately to assemble. And our needs, there are you start with the primitive ones, and once they're satisfied, you move up a scale. To me, I thought perhaps that security, then comfort, then convenience, in terms of once you're secure and comfortable, you start thinking about how better to do things. What sort of environment do you need to do that? And then ultimately, perhaps satisfaction. Nothing's terribly clear-cut, but it seemed to me those were worth bearing in mind. And I think we'll manage to get back to those later. And then I wanted to start putting to those three elements, MAN, I put them in that order mostly because it was easy to remember, man, and we wanted to think about the red line here is the material line, and it's deliberately above and shooting off faster than any other line because I think that's where the major change and increasing sophistication has come from and is coming from. And so in the early days we start with raw materials of timber, stone, mud, which we make into bricks, so we're starting to have an influence on it, cutting it, ice of course. I mean, this is not in a serious time sequence. I have no idea whether Eskimos were doing what they do before the Arabs were building mud domes, but composite materials like wattle and daub. I just wanted to mark a few, the few key markers to a structural engineer, like the major use of iron that started to crop up during the Industrial Revolution. The Industrial Revolution couldn't have happened without iron for machines, and of course that influenced the building industry. And then ultimately that led to the development of steel, which was a much more forgiving material and usable for a far wider range of things. And then into the plastic age. I've zipped through 1925, which I'm sure those of you who read about these sorts of things seems to be the recognized date. I'm sure there was a publication then of quantum theory, which seems to be quite a key point in terms of understanding, which has helped lead towards new materials. And on we go, crossing the boundaries into something. There are other things we could talk about, but I find the word nanophysics quite tempting and seductive. I only really started to realize that physics was moving into a new micro dimension, the nano dimension, because the UCL around the corner is putting in a grant to build a building to enable them to research in that field, and it seems to be a very well funded field. And so I'm beginning to get to grips with what nanophysics is all about, and hopefully I'll say a little more about that later. But revolutions in materials seem to be on the cards. Our understanding through quantum theory has opened up a whole new door of understanding. We all know about genetic engineering, the biological manipulation at a micro level, at atomic level. But in physics, new materials are being talked of in terms of two levels really. One is interfering at molecular level to create new materials, but also maybe at a slightly bigger scale, minute invisible magnets and motors which can start to make materials do things physically which would otherwise be completely unnatural. A very interesting area coming up. The M, we've done the M. The A, in terms of ability, so we start off in a rather crude way, talking to each other, using tools, feet for transport, wheel, cart, on to ship, timber, of course, we have ships, but moving on into steam power, aeroplanes. There's the quantum theory marker. Then, of course, into the computer age, the internet, the combining together of the globe as one big computer, which is a huge leap in ability. It just so happens to be a communications ability which will obviously hugely facilitate development and growth. Whether or not that ability is reflecting in our ability to construct is the thing that I particularly question. The way we build buildings has not changed all that significantly. Maybe it's something to do with the fact that gravity is a constant, but we're still scaffolding things out rather in the same way as we scaffolded out 100, 200, 1,000, 2,000 years ago, and so on. So the means by which we actually build are still quite simple. Don't want that one. And again, in time, one likes to think that in the early days, caveman was mainly interested in security, considered themselves quite fortunate if they found any degree of comfort. But as time goes on, not only are we looking for comfort, but we're trying to get ourselves air-conditioned, fully ventilated, etc., for convenience, to be able to do our job well. We start to have higher expectations. And I have this kind of feeling that I want to look at a bit later on, that perhaps we may be entering an age of greater satisfaction in terms of the built environment, and what that means, satisfaction in what terms, is worth looking at. So now it's on to slides, which, with a bit of luck, that switches us on. So a quick glance through history. So that graph kind of did a historic sweep to try and pick out what it was I thought was interesting about these trends. What I find quite interesting as a structural engineer is the way that form, the shape of buildings, has been influenced by the materials that people have had to live with and their ability to handle those materials. and ultimately also the needs that they were trying to satisfy through that building. That's slightly secondary. And of course we start with base materials like stone, natural formations in compression arches. Stone is an obvious compression material, and the form that it most easily carries load in is compression, which is columns and arches. And initially one doesn't need any tools to live in a cave, so that makes sense as the first primitive dwelling. Another compression material being ice. If you don't happen to live it convenient for a rock formation, maybe you live on the pole and can hack around at pieces of ice. But there's no way an Eskimo is going to be building out of stone any more than someone living in the Sahara is going to be building out of ice. It's quite interesting. On the left, there's a very, very neat-looking pile of ice bricks. I always get the feeling that's for the tourist photo. And then on the right, that's what they really look like if you have to live in them. And then, of course, if all you've really got is mud, then you're going to be stacking. You're going to be making bricks. So you're starting to take the mud, use the heat of the sun to create little precast units, and start to invent ways of not just piling them one on top of the other. I mean, they're very easy things to pile one on top of the other, but that's not. You can't really live in a wall. So you have to find the best way of enclosing a volume, and it wasn't long before people realized that if they were very careful about it, they could form arches and domes which did enclose volumes. And if you live in a mainly woody area, then you're going to start looking at what you can do with sticks, what you can do with straw, what you can do with animal skins. And this is the first picture of a framed building rather than a building which is thought of in terms of a stack of compression lumps. And this is it's just worth thinking about. I mean, it's hardly fair to call these lintels on top of these columns beams. They're really just hidden arches, the lines of thrust hiding inside the thick block. But anyway, it looks like columns and beams rather like Stonehenge. And so it's just to make the point really that even primitive use or simplistic use of stone, not call it primitive, doesn't have to show an arch form. And then people through the ages have started to get very inventive and very clever. This isn't always exactly structural stone, to be fair to it. It's often just false ceilings hidden behind a rather ordinary roof. But what people could do with bricks and stone in compression, when their ability started to move forward, they were communicating, they were travelling, they were able to spend more time thinking rather than hunting, and they became very, very inventive. Not always with great total success. There's a long history of failure of cathedrals through trial and error, and what they started to realize was that simple curved forms, simple arch forms might carry vertical load for a while, but eventually if you keep going up and up and up, you start to get lateral thrusts which aren't being carried successfully to the ground, and so the flying buttress was invented to hold the vertical walls vertical, or if you prefer to see it the other way, let the line of thrust crashing across the diagonal find ground. And then timber, I suppose this is the start of the idea of framed buildings, framed houses, framed roofs. Timber is a rather mixed material. It can carry a bit of bending, it can certainly carry compression, it can even carry some tension if you can work out how to hook into the timber and give it a pull. And so people started to enclose quite large spaces with sticks and beams and posts and ties, and that generated an architecture that we're kind of familiar with in this country, where of course we've had forests for a long time. And then the crunch comes. We had metal ages way before this, but not the ability to build, to create iron at the volumes that became possible in the late 1700s. And of course the famous bridge at Iron Bridge was one of the early demonstrations of the use of cast iron, trying to concentrate on keeping everything in compression in the traditional arch form, because I think people recognise that it was really a material best used in compression. On the left we've got a picture of the reading room at the British Museum, which is during construction, which you probably know that over there now there's a major project near completion, and we needed to try and find out quite a lot about it before we started to dig a 2-story hole right the way around it, and this photograph was very useful. It's a mix of cast iron and wrought irons being introduced a little later after cast iron, with better properties, more capable of carrying bending and tension, and so it started to open up the possibilities of using metal, using iron, for buildings like this. Famously, also on the right, of course, a Crystal Palace, early ships, and so on. Through this, ultimately, the discovery of steel. One of the big openings, not only is steel a highly more forgiving material in carrying, not breaking under tension. It's actually very good at carrying tension as metals go, and opened up the field for tension structures, but particularly initially tension cable bridges, suspension bridges. And then, of course, wide-span structures, the Exhibition Hall in Paris, and let's not forget that, of course, it opened up a whole world of automobiles, aircraft, and so on. And with steel, people could start to use it to replace the old timber floors, and really treating it rather like they would have treated timber, but with that strength, being able to build much higher. And it's fascinating, this mill outside Paris, which I think was a chocolate factory. Other people might know more. Looks incredibly like an old Tudor house, the way that they've used the framing, but it's actually a steel carcass. But it completely opens up the world of the buildings that we've known in this century, and the flat slabs. And then, of course, we mustn't forget the role of steel even in enabling us to build in concrete. Without the reinforcement to most concrete structures, they wouldn't be there. But there were interesting developments going on in concrete much the same time as there are now. And it enabled structures like in transport, like the Zeppelins, and then it moves on to a point that I want to sort of pause at again, where the search for lightness in construction, extreme lightness, and an interesting point that really with Buckminster Fuller's domes, he was confining himself to pretty simplistic shapes, perhaps because they were easily built, rather in the way of the old brick domes. Perhaps also because he felt that they were very efficient. I know that it was important that the sphere is the lowest surface area for an enclosed volume. That was probably important to Buckminster Fuller. But there was a certain constraint on what people were able to do, or willing to risk doing. But we're talking about very lightweight structures. And at that point, if we can just pop on, if that works, and then this works, yeah, to look again at form. So we've got to a point now where lightweight structures are possible, using steel and using skins. I want to sort of think in terms of natural forms and willful forms, because there are many ways that, having opened up the forum with the materials, that we can build. We can build tension forms which are natural catenary shapes under a weight, say a suspension bridge cable, or we can willfully pull them into it, distort them into another shape. But if we want to hold them in that shape, we have to continue to apply that force. So it's not always satisfactory to, tension forms aren't always the most amenable to letting us invent complex shapes. In the next few slides I'll be looking at various tension forms, and I just want to sort of help illustrate what we're going to see with these thoughts. So they're not tension structures have a somewhat limited vocabulary, unless you're willing to do a lot of hard work in pulling and twisting and hiking them into positions. Compression forms are a little forgiving, but not very. A pure compression form, like an arch, if it's not going to carry bending, you've got to be very careful about make sure the arch is thick enough to hold the line of thrust inside, and that's quite limiting. You can't start to distort your arch very much before it breaks. Pressurized forms, air houses and so on, they're a bit like tension structures. We're talking about a tensioned membrane that's held into position by a pressure, internal forces. They're actually radial as opposed to vertical, shown here. And if we want to distort that into new forms, inventive, interesting forms, we're going to have to pull counter to that pressure, or we're going to have to put in a rigid frame, which is rather counter to the whole idea. So we have to put in diaphragms, we have to put tubes in, we have to do quite a lot of work to make interesting forms. And I've got some slides that I want to show you about that too, because there's a lady here doing research at the Royal College of Art who's been doing some interesting work in pneumatic forms. Oh, there's the push. And bending, the point is that it's not that surprising that the most exciting forms that are coming out at the moment seem to be structurally quite dull. They're bending structures. They're structures that are capable of taking very complex forms by using forgiving materials like steel, which you can bend and distort into all sorts of shapes, and it'll find a way of coping. That's not to underplay the role of an engineer in making sure that it's strong enough to carry the loads, but it will build up stresses like that, and it will have to get thicker to deal with that. It will have to be strengthened and so on. But I think it's interesting to look at, as we're now going to look at some slides, the way that tension structures gave a lot of new exciting forms to us in the 60s, 70s, 80s, 90s, but that the really exciting structures now are rarely tension structures. And I think that's probably best described as a pity when we start to think about environmental minimum use of materials, environmental aspects, and the possibilities of using less materials, the possibilities of buildings which we want to move to respond to the environment. There's a lot to be said for lighter weight tension and inflated structures that I think we need to push further. But meanwhile, back to the slides. So, on from Buckminster Fuller, we're into the age now really of plastics, the ability to put skins on very light frames, whether it's a Buckminster Fuller compression dome or a Friotto tension roof like at Munich. And here, in a fairly simple way really, sheets of acrylic fixed onto cable net. Early plastic cladding. Here's some of the sorts of things that happen with tension structures, the limitations on form, where generally speaking, to get a tension structure to be stable under wind load and so on, you need to develop a double curvature, and you end up with this language of double curves. The technology, the ability that we've been talking about, came through computer technology, early computers which were able to define lengths, find surface structures. That was very, very important to open this door as well. But the language was quite simplistic. We've got trying to show the fact that one important point about tension structures and inflatable structures that we mustn't forget is they're relatively straightforward to construct, because rather than, talking in general terms, rather than all the scaffolding that we see on most building sites, it's something that you can assemble on the ground and lift. That's a lot safer and it's a lot quicker. So there's another virtue of membranes rather than compression. Other forms, this is a slight strange hybrid that I'd always think it's worth showing, because although this is a cable net structure in Hong Kong, it acts as, really the cable net was used as scaffolding from which to hang or pour concrete into formwork, which was hanging off the cables, and you end up with this lattice, this curved lattice, which acts as a dome. So it's this strange hybrid. Moving on into further hybrids, really advancing the idea of what other forms can you find with membranes and with tension, and also using this great advantage, as you see on the left, of being able to connect together on a level and then lift into the geometry that you want, almost by magic. These are woven net aviaries. This one's in Hong Kong, and it's a strange hybrid, really. It looks almost like a compression structure, but it's actually the woven mesh is carrying load by double curvature in tension, and the volume is created by hauling up the net into stressed points. It's really rather like the dome down in Greenwich, where you have 12 giant masts, almost pretending, like acting like skyhooks or acting like negative pressure, in order to force the shape, which is not a tension structure shape. To have a self-closing form like that is a very unnatural thing for a tension structure. So the cable net is tensioned into position by these 12 skyhooks and radial ties. So it's really it's the sort of big brother of one of these structures with a rather simpler geometry. And another one with and without its snow cladding. And so the dome I always find is a very interesting hybrid, because it's really an air house. It's really trying to be a membrane fixed to the ground and then inflated. For many reasons it's not an air house, but the efficiency of using membrane structures which are held off the ground by an infinite number of fingers of air pressure pushing up on it, the efficiency of that shouldn't be underestimated. And I like to think that air-supported structures do have a future. It's hard to imagine something so efficient, so requiring so little material, so easily covering huge volumes, and therefore enabling us to modify our environment in such a dramatic way, so cheaply, anything as dramatically as an air-supported structure. There have been many projects for the last 20, maybe it's 30 years now, to cover very large areas. Originally, Arabs had a project looking at covering a city in the Arctic, and this one here a little more recently, still in the 80s, to cover a township in Canada. It's phenomenal what they're capable of doing. If you then try and make them interesting, it starts to get more difficult. Early attempts to be interesting This is fascinating as a piece of engineering, by the way, but which I won't go into, but quite difficult to not make them look like Mr. Blobby. Some other interesting historic air-supported structures. Expo 70 in Osaka was the sort of most important moment, it seems, for air-supported structures. Inflated tube structures and inflated cushion structures, the Pavilion of the Sun on the left, a part of the sort of radical spectrum of things that were being done. And the inflated cushions there back in 1970 are sort of the forerunner in polythene of what I imagine you all have seen now of the inflated ETFE cushions that are pretty successful now at replacing glass, both for economy and to allow it to be fixed to flexible supports like a cable net. So those being air-supported structures, the next move on, in my mind, is rather than using pressure to form, to hold up a membrane by, as I said, a sort of infinite number of fingers pushing up. Perhaps there's ideas like this at Mannheim, again done in the 70s, using if you like, a preformed timber lattice, infinitely pushing up the surface. And this is generating a very interesting organic shape in a way that would be very difficult, just about conceivable in an air-supported structure, extremely difficult in tension structure because it's a closing dome shape. And in those days, back in the 70s, computer power was pretty weak. Certainly, Friotto still felt that the way to define the form was through a hanging chain model. And although I haven't shown you this, I'm sure you know that the hanging chain forming a catenary is a natural pure tensile form, and so that if you invert that to through 180 degrees, turn it up, the same form is a pure compression form, provided the loads are vertical and uniform. It starts to fall apart a little if the loads are not vertical and uniform, like weight, which of course wind and so on isn't. And so you still need to introduce extra rigidity, perhaps even a little bending strength to deal with non-uniform cases. But a fabulous product of that ingenuity, really rather checked by computer rather than designed by computer, and ultimately checked on site by hanging dustbins full of water in them. So technology just really moving into the computer age. More recently, really not exactly moving forward, but more recently and more easily developing the same sort of ideas. We've done one or two projects around this country, and there's an exhibition hall in Germany happening at the moment. Similar ideas. Now, a very important thing that I didn't mention back on Mannheim is of course that we're still just hanging on in the realms of buildings which can be assembled on the ground and then hauled up, like the membrane structures and the cable net structures. These lattice structures can be assembled on the ground as a flat lattice and then hauled into shape with angle distortion between the lattice by rotation at the nodes, allowing the shape to be taken up, thinning down and fattening out. So we're still in the realms of the easily buildable. It does start to be more difficult to use these sorts of techniques if you've already got buildings underneath getting in the way. It's rather nice to have nothing in the way so you can lay everything out flat on the ground. But certainly at the Hong Kong aviary, there was a dirty great valley and river and trees in the way, and so they had to build a scaffold deck. So slightly lose the argument of not needing scaffolding, but the principle's there. Here's another easy to erect building I thought was worth throwing in. We're trying to talk about natural forms. I haven't really dwelt on it for long, but the tension structures and the tension structures basically formed. The forms of a tension structure can be determined by allowing the levels of stress in the form to define the shape. This is why Friotto and others used soap films as a modelling method to find out what were the right, most efficient, least material, stable forms for tension structures. A soap film would automatically take up a surface shape of minimum or of uniform stress. And a similar sort of idea with the hanging chain model, always using physical laws through physical models to define your form. And in a way, by not taking the easy route through computers and having to use natural modelling, the modelling was quite simple and might not have given that amount of freedom in the type of forms that were generated. The only way to get that freedom was to play with the edges, was to lift points and so on. So it gave a limited vocabulary, but it did encourage people to generate natural equilibrium forms rather than forced forms, non-equilibrium forms that we're tending to see now. But here's another natural equilibrium form where timber thinnings out of the forest are taken initially straight and then simply bent, and the arc of curve that they take naturally is rather curvy at the top, at the tip where the tree trunk is thin, and then rather straight at the bottom where it's stocky and anchored into a concrete beam. It's, in ecological terms, a very simple and sound way of building, except for the foundations, which seem to be enough to sink a battleship. And not to forget the importance of the plastics, the importance of finding a cladding material that would can easily be tailored to fit those sorts of complex shapes. Quite a limited palette at the moment of membranes that can do that. I thought it was worth mentioning the building over the road. It's a more complex form, rather like Mannheim, but erected and clad in a more traditional manner. It's not possible in the confines of the Great Court to try and erect a lattice structure to derive a complex form. And so this has been erected in a fairly well thought through way, which I'd better not bore you with, but having to install a full crash deck across the whole courtyard, and setting up, forming the geometry from a rigid base is probably the best way of describing it. But in terms of finding the form, computer power came very much to the fore, because we weren't able to. We investigated using soap film type models, again using the computer rather than real soap film, but the forms were not at all what we wanted. And of course, as you probably know, there were planning regulations about the height which had to be met. So in the end, it was a fairly forced form which was derived from a pneumatic form, but then constrained in. So we get a fairly non-uniform range of compressions around the shape, but the overall impression is of a very organic form, which gives us, through the use of computers, has enabled us to play with curvatures, radii, to ensure that the levels of stress are always within the bounds of the materials, and that we've been able to use fairly small, light elements. And another project that we've just been doing recently, looking at, again, at moderately complex forms. The point I wanted to make here was that, again, not possible to go for a form which was erectable from the ground, not least of all because when this is built there will be 3 buildings on the site already, so we have to build around them. But also in terms of the simplicity of the ability of contractors at the moment to cope with the idea of taking a flat lattice and lifting it at this scale, it's probably going to be more expensive. So on a project like this, we've actually had to develop it down to a very simple kit of parts. I just see if there's another slide, I'm not quite sure. No. So a very simple kit of parts which can be understood and erected by traditional contractors, and that they won't be frightened off and overprice it. So the slide on the right shows you that underneath that multiple curved skin, we have a primary girder lying in the valley, secondary beams on identical arcs running between those girders, and then a lattice of tertiary members and diagonals to stiffen the whole thing. So the whole thing actually acts as a shell ultimately, but getting it there had to be a kit of parts very much in the traditional manner of building a B&Q shed, just to keep the price down. But I think I've rubbed it home quite enough, really. The limitations of tension forms, and to some extent bubble forms, pneumatic forms, and compression forms, has forced us into, I'll get there in a second, has forced us into, there we go, those were the ones I was looking for, of the other ones of Gateshead, just to show it's really showing the rules which generated the geometry, again rationalized down to be quite simple from an erection point of view. But I wanted to sort of now able to move on, if you like, to the future, where I think we've sort of broken away from trying to use natural laws of physics to define our forms. We've got the computer power. I'm sorry, I'll leave this on for a while if you like. Computer power to generate whatever surface we like, really, and let someone else worry about how to build it. And yet the problem that it confronts us with is that it doesn't always have a simple erection method. It doesn't always involve minimum use of materials. We have to strengthen, we have to stiffen, we have to work very hard to create some of these curves. But on the needs side of the MAN, maybe this is what we're talking about in terms of satisfaction, because maybe just going for natural forms isn't enough. Maybe we need to look at nature not so much about telling us how to build, but what is it in nature that makes us satisfied with our environment? What is it that will give us pleasure? And I was very thankful to Judith, who told me something that I'm sure everyone else knows, but that there is a very large part of our brain which is devoted to, or does the job of, differentiating subtle changes in nuance of curve. I guess primarily in faces, that's what I understand, but I mean, I'm sure it obviously in anything, that we're very tuned to looking at each other's faces and recognizing the importance of subtle changes of mood and messages that come from that. And we're obviously in many of the objects of everyday life very used to being very receptive to much more curved forms. And as an engineer, it's taking me a while to catch up with that thought, that it's perhaps an important part of satisfaction that's missing in a lot of the built environment, that we need to not ignore. And obviously there are many people not ignoring it. And a few of the projects that we've been lucky enough to do, not many built, but that we've been exploring, like the Museum of Sex here in New York, which takes its inspiration from the slide on the left, or something similar, really starts, without getting hung up about why the form is as it is, it's an eye thing, it's a brain and eye thing that determines it. And this is slightly different. I mean, this might not, but I see this, the body by Nigel Coates in the dome. It's the first time I've been involved in a project really which started absolutely clearly as a piece of sculpture. We still have a piece of the sculpture in the office sitting there, and it was very carefully eyed for its curves, and there was no compromising that. There was no engineer saying, oh yes, but that's not a natural form, I can't do that. It was simply a piece of sculpture that was going to become a building. There may be more of this. And we tried, obviously, to find an erectable, logical, simple way of putting a structure to this, bearing in mind people were going to be inside, it had to be treated as a building. And we found physical models, back into physical models, absolutely vital in terms of communicating to contractors that it was really going to be rather easy in spite of everything, and that it could be broken down into a kit of parts and all that stuff. And again, so how it was going to be assembled and erected became an absolute key point to being able to achieve it. It was the biggest hang-up. We all had the computer power. We were all banging emails to each other. We were firing all the information straight down the line to the fabricator, etc. But putting the damn thing up on site couldn't possibly be forgotten. Also, skinning a thing like this and achieving the very subtle curves, the nuances of shape that Nigel Coates was looking for, did involve other technologies. The steel alone, the carcass of steel underneath, couldn't be taken to the shape. It would have been far too complex. So there's an in-between layer of sprayed fibre reinforced plaster, which isn't a great way to go about building buildings. The buildings of the future probably can't afford this unless the technology becomes simpler. And then there's a couple of projects I just thought I'd throw in. I mean, they're probably not the obvious choice, but a couple of projects with Greg Lynn that our New York office have been doing, neither of which are going ahead. This is Cardiff Opera, with Greg Lynn, and the other one's the Yokohama port, I believe. But these subtleties of form that we're now having to achieve with no real recognition of natural forms. We're dealing here in bending shells, distorted steel with a skin on. But maybe for the satisfaction, maybe that's what we have to do. Anyway, what UDIT's been looking at, as I mentioned in the RCA, we're now moving further down into the future perhaps. She's actually looking at pneumatic forms with an eye to what those pneumatic forms might tell us about other forms. Maybe we're not always talking about building pneumatic structures, but exploring shapes with some natural rules applied, not complete abandon of nature, complete abandon of force, nor even complete abandon of how it's going to be built. And maybe there's potential here for finding a way forward that's not quite so forced and false. And she's been investigating all sorts of curved forms to create theatre spaces, furniture, and so on. And the sort of heading towards the sort of ideal state of satisfaction on the needs curve. Are we right in thinking that it's actually rooms like this that are really where we should be? What are the sort of parameters that is it just about our use of materials that says, well, we build in brick, so we build vertically, and then we build in concrete, so we build horizontally? Is that what it's about? I mean, I know furniture tends to have to sit on flat floors, so there's a sort of dilemma there. I'm not sure we've got the environment now. I have a feeling there are big changes in the environment that we'll be living in and working in, perhaps certainly in the next 100 years, which will come out of the way we use new materials, apply our new ability, and start to perhaps reinvestigate our needs. And I think now we need to bring in what nature does, because we haven't really talked very much. We've talked about natural forms, but I think we've now got much more understanding of the importance of our environment in moulding the type of buildings we live in and the way that those buildings respond to the environment. And I think it's the new technologies that are coming around the corner, which will enable us to be much more sophisticated in our materials and in the way our buildings respond to the environment. On the right, there's a a section through bone, just to remind us that bone is the sort of material we really want to be building from, but live bone, which actually understands the levels of stress that it's under, and over time, admittedly rather longer than a normal building site, but over time concentrates its strength and its substance in the area which needs it most. And you'll find if people are cut open, they can tell the sort of life you've had by where the forces have been going in your body. If you lean a lot, you'll have a stronger bone on the side you lean on. Nanotechnology might even lead us to materials like that. It's all a bit idealistic to think that the construction industry is going to be a leader in this. We're always tailing behind new materials. We tend to pick up what's chucked away from other people. So the medical industry, aerospace, and so on are the places we need to be looking for snatching and using materials that they're plugging the money into inventing. And this is the nearest I could find to a flower opening. I mean, buildings which respond to the environment, like a flower will, trees which bend in the wind, flowers which open when the sun's out and close at night. This sort of flexibility and adaptability of buildings is something I'm sure we're going to see a lot more of them in the future. And that flexibility, as I mentioned before, is going to come much more easily back in the field of membrane structures, inflatable structures, and so on, where the structural system isn't rigid; it's variable. So that's why I think the sort of work that you did, and probably many others are doing, is really worthwhile. Symbols of the environment, really, just to remind me to the use of wind for power, the use of the sun for power, things that we're obviously becoming quite increasingly sophisticated at doing, and work that a company called Festo have been doing on artificial muscles using air pressure. It's a game, I think, for them of publicity, but really the potential, just as an illustration of the potential mechanical things that are starting to be available. They might be being considered perhaps more for robots and for huge money-making machinery, but the potential it will open up slowly to the building industry for making elements of buildings move, opening, closing, and so on, is great. And that leaves us comes on to the last project, really, which actually Neil knows more about than I do, and so this is going to give me a chance to ask him to say a few words before we shut up. Maybe I'll shut up immediately. But this is, for me, this is an interesting looking building of the future. It almost combines the sorts of things that I've been trying to lead us towards. Membranes, movement of the building, adapting to the environment as the environment around it changes. In the future, with the help of nanotechnology developing materials, mechanically adaptable materials, the materials themselves will change to suit the environment. So this is a totally non-static piece of design. Okay, well, I'll just ask Neil to say a few words.
Thank you. This is the only project which I'll really refer to, so we won't keep you too much longer. But before talking about this, I just wanted to mention that for my discipline as an environmental engineer, one of the things that we must always be striving to do is to deliver the best quality space, the best environment that gives us the highest comfort to live, to work, and to be within. And that's really the whole thing that drives the way we work as environmental engineers. In order to do that at the moment, we need a degree of energy to temper and attenuate the natural environment that occurs around us, which doesn't really suit the way we always want to work. And as I'm sure many of you know, the amount of energy that we need, well, half of the energy that we actually produce goes into sustaining the environments within the buildings that we're in, for example, this evening, and all the other buildings that you've been in today, yesterday, and you will be in tomorrow. So nigh on 50% of the energy that this country, in fact this world, produces is used to sustain buildings and to create an artificial environment in which we can exist. Now, at the moment, it stands that we can carry on doing that, and we can carry on using the energy resources of the globe to do that for us. And the predictions are that for the next 200-300 years, we could carry on like that. But that prediction relies on two things. It relies on the fact that there are X number of people on the globe at the moment, which is clearly going to change, at the moment, exponentially. It also assumes that we will remain satisfied with the type of environment which we've grown used to at the moment. Clearly, as Mike's curves earlier showed, we're always expecting more, always expecting better, always needing something else. So if you play those two factors into account, the exponential growth of population and the increasing demands that we're going to expect of our environments, then the energy left in the globe is 100 years, 50 years, something like that. Our generation or a future generation within 1 or 2 generations is going to need to solve this problem. And one of the things that I have been looking at more closely is emerging technologies, and in the same way that materials help evolve structural solutions, the way in which we produce energy might help resolve some of the issues that I have to face. At the moment, we haven't really cracked it. I think it's largely because energy, oil prices and so on have been so cheap. There's no real impetus to change from where we are until such time as carbon taxes and things come into being in real force. And I look forward to that day, actually, because it'll really focus our minds. At the moment, there are technologies, fuel cells and so on, which are emerging using hydrogen and so on, which produce clean, easy-to-use energy at the right grade and only produce water as a byproduct. At the moment, that technology is expensive. It's not exactly efficient because it takes a lot of energy to produce the hydrogen in the first place, but it is perhaps a way to move forward into the future. That perhaps isn't the realm of the construction industry to develop those technologies, but we certainly will rely on them. So we've been turning our minds towards the way in which we can better use what we have at the moment, and there's a lot of talk about intelligent buildings, intelligent facades. But it struck me that actually a lot of the technologies and facades and things that have been developed in the last 5 or 10 years aren't necessarily intelligent. They are still pretty inanimate sort of things. They sit fairly dumbly on the earth, and they allow the environment to move around them, and they only really react accordingly. They don't actually do a great deal other than attenuate the changing environment around them. What we're wanting to look for, and this project gave us a great opportunity to take it a bit further, was look at buildings which can actually have more than an IQ. They actually had an attitude. They actually, instead of just sitting there relatively dumbly and absorbing energy and reacting to things, they actually went and got it. They actually did something with it. And not this project, but another, a museum project we looked at in Germany. We wanted to propose a notion whereby the building didn't just react dumbly, but it went and got some energy, and that we could actually ration that energy on a daily basis as part of an educational process, because it was a museum, a science museum. And the idea was that we might actually just allow it a certain amount of water in the morning. We might just feed it a certain amount of electricity. We might just give it a certain amount of gas. And then, armed with the knowledge of what the environment was yesterday and what it's likely to be today, armed with the knowledge which you can process in BMS systems of how many people turned up yesterday and how many people are going to turn up tomorrow, because it's a Saturday, for example, it would then have to decide how it's going to reorganize itself and rework itself to best suit those needs. And those are the sorts of technologies, particularly with robotics, as Mike explains, that might lead towards buildings which have not just an IQ, but an attitude to go and do something with it. If I just explain this project here, it's a competition for an expo site in Switzerland, and it sits on a lake. Only a portion of it sits on a lake. The large, on the right-hand side slide, the largest part of the exhibition is in a series of pavilions on the land. But there was a pavilion which we were able to put onto the lake's surface. And the way we developed this was that it was to be a sort of an organic structure that was related, the universe and I, to an experiential sort of event. This structure was developed as a pneumatic structure, and it's developed as a pneumatic structure because it sat over water, and as any air-inflated structure has a problem with sealing its edges. So we were able to develop a technique of putting gabion baskets in just below the water's surface, pulling very simply fabric over that and pulling it down just below the water's edge and then inflating it. And that seemed like quite a quick way to put up an expo centre. But us, with the architects, it was Lifshitz Davidson on this, developed this further to the point where this building began to have a bit of an attitude of its own. On the left-hand side, you can see in the middle a rather sort of curious curved shape protruding through the middle of the volume. And the idea was that that had on top of it a lens, and that lens could adapt to the sunlight and could actually blink. And further pneumatic structures would enable that eye to open and close depending on the experience that was required inside. If it was a show, say at the Millennium Dome, it might close its eye to give a background of darkness for the show, but during the rest of the day it might actually open. And that gave a sort of sheath inside of skin which was acted as a conduit, much as the optic nerve conveys light senses to your brain. And then we figured, well, actually, this thing probably could do with breathing a bit. And rather than just mechanically ventilate it or use the fans which air support it, we thought it rather looks a bit like a lung, so we'll give it another organic dimension. We'll make this thing breathe. The whole structure was contrived, therefore, to use that same sheath, that same optic nerve, using tension cables that allowed us to winch them down, so the whole structure remains under pressure, stable against wind and snow and so on, but winch it down, thereby reducing the volume of the entire enclosure. And that way the building would exhale. As you slowly release the cables, then the air fans which are supporting the structure will slowly introduce fresh air back into the building. And that would then re-inflate the structure. This isn't particularly new because it's actually how gas chambers work. The big gas drums that you see around about are pneumatic structures that actually fall under pressure and climb again under pressure. But this way we could actually create the building that acted as a huge lung and pumped and breathed. And so it created a sort of diaphragm effect. So we had this thing could see, and it could also breathe. We weren't really happy with that. We thought we'd go another step further. This has a south aspect and a north aspect. So we would use the lake water and pump that up and trickle it over hairs on the surface of the skin and actually use that for evaporative cooling. And so that was generating the sweat on your skin. And for that purpose, we could actually combat, a good chunk, a good 30% of the actual solar gain that was trying to collect in through the south-facing portion of this skin. So it breathed, it saw, and it sweated. And we thought, well, we'll give it a bit more dimension. And on the north side, we then tried to create, it has a very strong north cold winds for part of the year. So we put more pneumatic structures up on the other elevation. And we were able to inflate those again, fairly simply, pneumatic structures, and under cold winds, when we were able to sense the temperature, sense the direction, sense the wind speed, sense what was going on inside, and we could actually create a stable air layer, which was a laminar air layer trapped next to the skin and allowed the turbulent air layer to move over the top, and actually create a sort of wetsuit type skin and trap an air layer on the north side. So it had a certain insulating properties as well. And by that way, we were able to begin to put together something which was much more organic, much more biological, and hopefully something which began to have a bit more of an attitude. We took it a couple of steps further. We never really studied this in too much detail, but we were kind of enjoying ourselves by then. And we thought, well, this thing is a lung, we need to generate good quality oxygen. So we were planting reed beds around the outside. The reed beds around the outside would digest the effluent from the building and from the catering that was going on inside. And at certain times of the day, as you know, plants will give off oxygen. If oxygen and the reed beds were in the airstream of the air-inflated structure, then we would be introducing the oxygen back into the building. And then we thought, step further again, we'll make the blood cells inside this thing come alive a little bit, and we would actually feed the water within the exhibition. So we were going to occupy the water contained by this exhibit, by this pavilion, with live fish. And the fish would act as the blood cells within the organism, move around, actually clean the water and act as sort of scouring agents for the internal environments. So really that's about as much as I want to explain about this particular project, but it seems to me that if we need to wait for other technologies, robotics, manufacturing processes, fuel cell technologies and so on, to give us those energy sources to continue to sustain our population and to continue to improve our quality of environment, then the very least we can do is start to think about the way we can make buildings that much more reactive, that much more intelligent, and hopefully that much more with an attitude to go and do something about our future. So with that, I think I'll sort of finish and move Mike to close up.
I'm not sure I don't think I really need to follow on from that, because I think Neil did a very good summary there. I do have one more, if I'm very lucky, one more of these things, but there we go. Just to, as a sort of summary, if it's going to behave itself. Maybe it won't. In which case, doesn't really matter.
Don't know where this.
Well, anyway, I can remember. Oh, right. Technology will warm up quietly in the background. It's not a very interesting graph. It was just to sort of summarise this business, just to remind ourselves. I mean, I think the thing that Neil has brought in now matters the most. We talked about material advances. They're going to be huge. Some will be mechanical. In the long term, they'll be molecular. There's huge potential in there. Unfortunately, not in many of our lifetimes, perhaps some of the most interesting stuff. But and in ability, fantastic growth of ability that we've seen. Our understanding of our environment has grown. We're now manipulating it. We've invented a net of communication around the world, which is making huge impact. And I said at the beginning, the thing that we're not doing is increasing at the same rate the other part of our ability, our physical ability to defy gravity and build. And that's something, maybe it's robotics, I don't know, maybe it's about materials which self-grow like a body, but we're certainly, I feel like we're lagging in terms of buildability. And then on need, this is where I think Neil's point is crucial. It's all very well to talk about comfort, convenience, and satisfaction, and indulge our satisfaction. That probably is important, but at the end of the day, I think we're moving into back into a sort of survival need, with the having to consider the impact of what we're doing on the planet and moderating what we do for survival. And that's where making our buildings intelligent, maybe they can be satisfying at the same time, but making them intelligent, using intelligent materials, is perhaps going to satisfy the biggest need of all, which is survival. That's one way of ending. So that's it. Thank you very much, and I hope you enjoy it.